Okay, so we've been talking about RRKM theory. And we used RRKM theory to determine the rate of photodissociation or a photochemical reaction as a function of the excitation energy. Okay, and so what I want to do today really quick is just relate the rate constant that we obtained using RRKM theory at a fixed photodissociation energy with the rate that we obtained using transition state theory, which was for a well-defined temperature. So what is the relationship between the RRKM rate constant and the thermal rate constant, which we got using transition state theory? Okay, and so if you have a rate constant that's defined for a particular energy, but instead you want the rate constant for a particular temperature, then you can calculate this one in terms of this one by averaging over the Maxwell-Boltzmann probability of each energy, right? So K of T, we could write that as an integral over all energies. So from the excitation energy goes from 0 to infinity. And we want to take this quantity Ka of E star, right? So what's the rate at that energy? And then we need to multiply that by the probability of the system having that energy when it's at a certain temperature. And so we want, so for now I'll just call that P of E star, right? This is the probability of having energy E star. And we want to integrate over all possible energies. And so what is this P of E star? What is that going to look like? What do we want to substitute here? What's the probability of having a certain energy? If you're at a temperature, what's the probability of being in a state with a certain energy? Yeah, just a Boltzmann factor. And then, well, the Boltzmann gives the relative probability, and in order to have a normalized probability, you then have to divide by the partition function. So this P of E star, that's going to be, we need a degeneracy factor. And if you're in the limit where the energy levels are really close together, you can just take that degeneracy factor to be the density of states. So it's going to be the density of states at energy E star times exponential of minus E star over KT. And then in order to normalize, we have to divide by the partition function at that temperature. Okay, so if we substitute this in here, then we get K of T is equal to a integral from E star equals 0 to infinity of, okay, so I'm also going to plug in the value for the rate constant. So do you remember what that is? The RRKM rate constant, Ka, came up with a simple expression. It's just the total number of states up to the energy that you're exciting to, E plus, divided by Planck's constant times the density of reactant states. Right, so you count the number of transition states, vibration rotation states of the transition state up to energy E plus, which is the energy above the barrier, and then divide by the density of reactant states. Okay, so we're going to plug that in for Ka here. So we're going to get W of E plus over H times the density of reactant states. And then we multiply by this probability here. So times n star of E star exponential minus E star over KT divide by Q. Okay?
Times CDU
Yep, good. I forgot my variable of integration. Okay, so now you can see this density of states is going to cancel. The H doesn't depend on energy. Q depends on temperature, but it's summed over all the energy, so it doesn't depend on energy. So we can bring those out front. And then we see K of T is equal to 1 over H times the partition function. And then that's going to get multiplied by this integral. We're integrating from E star equals 0 to infinity. We have a W times an exponential. Okay, and it's going to be advantageous for us to rearrange this integral using integration by parts. And basically, so integration by parts, recall the formula says if you have the integral of u dv, that's equal to u times v evaluated at the limits of integration minus integral of v du. Yep, so this part's going to be u and this part's going to be dv. So if you, so how can we write this as a differential? Well, if you take the differential of this exponential, well, that's just equal to minus 1 over kt times the exponential, right? Times dE star. And so this thing here, this is just equal to the differential of the exponential times minus kt. So if we substitute that in, kt equals 1 over h q star times the integral of w of e plus right? So now this looks like something that we can easily do integration by parts on. And so, yeah,
Multiplied by something.
sorry?
Multiplied by.
Oh, sorry, I forgot my minus KT. Thank you. Okay, so this is equal to minus KT over H Q star. And then we take U times V, which is going to be W of E star, or E plus rather, times exponential minus E star over KT. Right, and so this has to be evaluated at E star equals 0 to infinity. And then minus the integral from E star equals 0 to infinity of the exponential of minus E star over KT. Oh, I'm sorry, I forgot sorry, let me back up. So, first we need du, right? So u is W of E, so what's du? W of E is the total number of states up to and including E star. So if we go a little higher in energy, how many more states do we get? Well, there's lots of states. We get, so it's going to be the density of states, right? How many states per unit energy times how much energy, how high in energy we run up. Right, so the derivative of the total number of states with respect to energy is the density of states, right? If we go up one wave number, we get the number of, how many states per wave number. That's the number of states that we increase by. Okay, so I can substitute here. Let me write this in a different order. I'm going to put n plus of E plus times exponential of minus E star over KT dE star, or yeah, E star. Okay. So what about this first thing? What's that equal to? At E equals 0, well, yeah, the exponential factor is 1, but how many states are there? At the zero of energy, there's no transition states yet, right? You have to go up at least a certain amount in energy before you start seeing transition states. So at E equals 0, this thing is 0. At E equals infinity, this thing is non-zero, but this thing goes to 0. So this first term here is going to be 0. Question?
In that part, we're not working with the differential of W. It's just it's V du. It's not. What I mean? Because when you substitute that formula in the last part, you consider.
So du is n plus times dE star.
No, but
and V is.
We should substitute W in there, not dW. Am I right?
So this is U times dV. So U is W, and dV is the exponential.
Yeah.
So du is the differential of w, which is equal to n plus dE star.
Differential.
Yeah. And then v is the exponential. Does that make sense? Okay, so this first term is 0, but then we have the second term over here. What about that one? That one is something that we have a definition for. Maybe you, so actually I forgot a bracket. So this kt over hq multiplies this whole thing. So, and so this is an integral of the number of states at a certain energy, or the degeneracy of states at that energy, right? Density of states at that energy times a Boltzmann factor. Maybe you're more familiar with this expression if this is a sum instead of an integral. But if you have a sum over degeneracy times a Boltzmann factor, what does that give you? That's a partition function, right? So this is basically the partition function, and we're taking the density of transition, so activated complex states, right? So this is the partition function for the activated complex. So if we write, if we identify this integral here as q plus, then this whole thing becomes really simple, and we get this is equal to, so we have a minus sign, minus q plus, so the minus cancels. We get kt over h times q plus over q star. And now this looks a whole lot like something that we talked about in the kinetics course. Right? What does this look like? Yeah, this looks like the transition state theory rate constant. So we used a slightly different notation before. We said the notation that we used before was we used these z's, where z was a partition function that has units in it with, the translational part of the partition function has units of per unit volume. Right, and so the notation we used was z double dagger, I not equal to 0. This is just reminding us that we take into account all degrees of freedom other than the reaction coordinate, which is what we've also done in our, we've implicitly also done that in the RRKM treatment, and then divide by the partition function for the reactant. Okay, and so we can see, so we could have derived the transition state theory expression directly from the RRKM theory expression. We didn't do it that way. First we did the transition state theory using thermodynamic and statistical mechanics arguments, and then we derived later in the course the RRKM theory expression. But if you take the RRKM theory expression and average it over a Boltzmann distribution of energies, then you get exactly this result that we derived before for thermal reactions. Okay? Any questions? We're going to cover this up.
this expression is only on pre-exponential factor?
Um, Did I screw up something?
Will there be an exponential part or not?
Yeah, there should be.
Professor,
Mm-hmm.
that E plus and E star is the same energy, or are they different energies?
Well, physically they're the same, but E plus is relative to the bottom of the, well, I mean, E plus is defined as,
E plus is smaller than E extra, right?
so it's physically the same energy, but one is relative to the reactant ground state and one is relative to the,
Yes,
Yeah,
I'm asking because in the integral I feel that they are different, but when you do the integration, you consider that they are the same. This is what I'm wondering.
yeah, I think it's the answer to the question. Yeah, so this is, this energy here, yeah, there's a mistake here. Thank you for pointing that out. So E star, that's like the activation energy, right? This E0. Right, we could call that the activation energy. Plus E plus, right? And so if you substitute that, this second term here, right, that's going to be minus integral n plus, well, so the integrating over dE or dE plus doesn't matter, right? It's the same amount, the same differential. So you can change this dE equals dE plus, and then this integral is minus exponential of minus E0 over KT times the integral of n plus times exponential of minus E plus over KT. dE plus. So then you get this exponential of E0 over KT. So yeah, that was missing. Sorry about that. And then this one is Q plus. Is that clear? So yeah, instead of doing the integral with respect to dE, or with respect to E star, just substitute E star equals activation energy plus the amount of energy above the activation energy, right? That's the amount of energy available to the activated complex. And then the E plus goes into this expression for Q plus, and the E star, or the E naught rather, comes out front. And then we get this exponential factor, which was missing. Oh, and I missed a minus sign. Minus E0 over KT. your textbook that's actually not really derived correctly. Okay, so I've told you all about RRKM theory. One thing that we mentioned earlier in the chapter was RRKM theory assumes that basically intermolecular vibrational energy redistribution, IVR, is infinitely fast, and that you're really sampling a statistical distribution of vibrational configurations. And it also assumes that there's only one pathway for the reaction, right? We assumed a particular transition state, right? But in fact, in real reactions, sometimes there are reactions that break these rules, and I'm going to show you some examples of that, or one example in particular. So we mentioned last time RRKM theory does a really good job at getting the rates of a wide variety of photodissociation reactions. So shown here was data for NO2 photodissociation, and as you increase the energy above the transition state, you can see that the rate of product formation increases. Okay, but another famous example of photochemistry is the photochemistry of the formaldehyde molecule, so H2CO. And this is sort of a general picture, what the potential energy surfaces look like for formaldehyde. So formaldehyde ground state is here. There's a very, very large energetic barrier associated with photodissociating formaldehyde to make the molecular products H2 plus CO. So H2 plus CO are almost isoenergetic with the reactant, but the barrier is really high. And a little bit higher than this barrier, I think this barrier is drawn a little bit too high here. It should be more like 70, 77, 78, something like that. But just a little bit higher than this barrier, there's another photodissociation channel that opens up where you can make the radical products. So you can also photodissociate to make H plus HCO. Okay? And so we're going to be considering the molecular product channel, but it can be influenced by this radical channel. So when you form the molecular products, this is what the transition state looks like. So the hydrogen atoms are sort of bent out of plane, and they're also over at an angle. So as a result, when this thing falls apart to make H2 plus CO, since the H atoms are out of plane, there's a torque along the CO, or there's a torque between this carbon and the hydrogens, right? Leading to rotational excitation of the CO. So you get high CO rotational excitation, and the hydrogen atoms are a little bit stretched relative to their equilibrium bond length, and so you also get modest vibrational excitation of the H2. Okay? And however, so if you go a little bit higher in energy, then you start to see a really interesting distribution. So there's a lot going on here, so let me kind of step you through it. So this is an experiment where, so it's a pump probe experiment. You come in with one laser, you pump the formaldehyde to 30,000 wave numbers, at which energy it dissociates. Okay? And then you come in with a second laser to probe the product. And in this experiment, they're probing the CO product. So they do REMP, right? Resonance enhanced multiphoton ionization of the CO. So you're detecting the CO in a particular state, right? Because the REMP is, you only get photoions when it's resonant with a transition. So you tune your REMP laser to a particular CO transition, and then if there's CO that's in the lower state of that transition, then you get CO plus photoions. And then you do velocity map imaging on the CO plus. Okay? And so you get, so in this first experiment, they're looking at J equals 40. So they photoionize the CO to look at the CO molecules that are in the J equals 40 state. And this is the velocity map image that they get. And so each of these different rings in this image correspond to different Newton spheres, which correspond to a different amount of total energy available to translational energy of the CO and the H2. So if you have a high amount of energy in the CO, that means that there's a very low amount of internal energy in the H2. And as you go, and so if you look at this distance and calibrate the velocity and then measure the energy, then it's the amount of energy that would be left over if you produce H2 in the V equals 0 state. Okay, so this outer ring means the H2 was produced in V equals 0. Then as you go inward, you have less energy available to translational energy in the CO product. That means more of the energy had to be in the vibration of the H2. So if you calibrate these energies, you can look at the translational energy distribution shown on a one-dimensional graph here, and you have a certain, you have peaks in this translational energy distribution, and they correspond to H2 in V equals 0, 1, 2, 3, and 4. Okay, and so that's what you would expect based on the transition state that I showed you, right? You get high CO rotation, and you get modest H2 vibration. But if you go to lower CO rotational energy, then you start to see a bimodal distribution. So this distribution of vibrational states of the H2 goes through a maximum here at like V equals 2 or 3, but then it goes through a minimum, and then it goes through another maximum at a higher V state. And if you calibrate the energies, you can see that this corresponds to V equals, 7, 8, 9, something like that, of the H2. And if you look at, if you do REMP on the CO fragment in J equals 15, then you only see these really vibrationally excited H2. Okay, so it looks like there's a bimodal distribution. There's two different things going on. And so if you kind of look at all the data together, right, you can do this for every single J state. So for every rotational state of CO, you get a vibrational distribution of the H2. At very high CO rotational states, you only see these low vibrations of the H2, right, from V equals 0 to 4 approximately. But if you go to lower J states, then you start seeing this second maximum in the H2 vibrational distribution. At very low J states in the CO, you only see these very high vibrationally excited H2 states. Okay, so what's going on? Well, so the very fast CO rotation and the H2, modest H2 vibration, that can be assigned to trajectories that go through, what you would think of as being the normal transition state. So you put a lot of vibrational excitation in the hydrogen atoms, and then they find each other and leave. And I'll play that again, see if I can stop it at just the right moment. Oh, stopped it a little bit too late. So backing up a little bit. Right, you kind of go through this transition state that is at an angle and it's a little bit off to the side. And then when that falls apart, it's going to make the CO molecule rotate. You only see a little bit of rotation in this video, but it's actually quite a lot if you consider, how many H bar. Okay, so that one wasn't supposed to play yet, but let me play it again. Okay, so what about this other distribution? Well, there were these other trajectories when they looked at these trajectories on the potential energy surface, where, okay, a whole bunch of energy goes into a single hydrogen atom. And oh, what's it doing now? It's like out in left field, it's in no man's land, it's just wandering around. It has nowhere to go. It comes around, it finds the other hydrogen atom, and then it extracts the hydrogen atom. Okay, so why does it do that? Well, the reason is because energetically, when you go right at the threshold, you basically only see the normal transition state. But as you increase the energy, you get very close to this other threshold for photodissociation to the radical channel, H plus HCO. And at the energy of this experiment, it's about 30,000 wave numbers. It's just below this threshold. So the hydrogen atom, if you put all the vibrational energy in a single hydrogen atom, it has almost enough energy to escape as an H radical, but not quite. So you try to make this H plus HCO product, but you don't quite have enough energy for the hydrogen atom to escape all the way. It's still attracted to the molecule, right? It can't get out. It's just going to roam around until it finds the other hydrogen atom and then extract the other hydrogen atom. And the way that you saw this trajectory, you can see there's a whole lot of vibrational energy that goes into the hydrogen atom and a much lower amount of rotational energy in the CO. So this is called the roaming mechanism, and it's sort of an alternative mechanism for photodissociation, and it's thought to be actually quite general for photodissociation reactions involving hydrogen extraction. So when you photodissociate an organic molecule to make H2, this is often sort of an alternative mechanism to the RRKM transition state mechanism. Okay, I think that's all that I wanted to show you on that. So we have about 10 minutes, so I'll get started on the next topic, but we'll probably have to finish it up next time.
Next Monday?
Yeah. No class on Friday. Okay, let me find. My screen is too small. Can't see anything. Okay, here we go.
Professor,
Yeah.
is this roaming mechanisms part of that paper from Bowman? No.
Yes.
Oh.
Yeah, Bowman did the potential energy surface on which the trajectories were calculated, and the velocity map imaging experiments came from Arthur Soot's lab. Okay, yeah, and this came out in like 2004 or so, and it was, at the time that it came out, it was like mind-blowing. People were like, that doesn't happen, I don't believe it. But then, since then, it's been found to be also the dominant mechanism in other photochemical systems involving hydrogen abstraction. Yeah, so it's kind of wild when it came out. Okay, so we've sort of covered all of the core material that I wanted to cover in this course on reaction dynamics, focusing on sort of collision theory, right? Energy transfer, how we calculate reaction cross sections as a function of impact parameters and things like that, right? So far, a lot of the examples have been gas phase reactions. Well, pretty much all the examples have been gas phase reactions, because that's where we really can uncover the most amount of microscopic detail about reaction dynamics. And so for the rest of the course, I want to focus on some other topics of modern research where we can look at dynamics of chemical reactions that happen in other environments. So I think the first thing naturally to talk about is what happens at surfaces, so interfaces of gases with condensed phase surfaces, right? Because we can kind of combine some of the ideas from these molecular beam techniques and gas phase techniques where we can really measure all the state distributions and energies and so forth. And then we're going to finish up with some topics in solution phase reaction dynamics. Okay, but first I'm going to talk a little bit about dynamics at surfaces. And the first topic that I want to introduce is, what does the potential energy surface look like for a reaction that takes place at a solid surface, so at the interface between a gas and a solid? And how is it the same, with the potential energies that we've talked about for gas phase reactions, how is it different? Okay, so, one of the most fundamental chemical processes that happens at a surface is physisorption or chemisorption. That means a molecule from the gas phase or from a solution or whatever comes in, it gets trapped in the attractive potential of the surface, and it basically sticks to the surface. Okay, and if you draw like a one-dimensional cut through the potential energy surface, just looking at the energy as a function of distance from the surface, then it has kind of maybe a shape like this. And so if a molecule or an atom is coming from the gas phase, so here I'm sort of drawing maybe an atom colliding with a metal surface, right? So if you come from the gas phase with a certain amount of energy, if you just consider only this 1 degree of freedom, there's no way that you can trap, because you're going to come in, you're going to bounce off of this hard wall, and you're going to leave again, right? So there has to be other degrees of freedom to which you can dissipate the energy in order for the molecule to trap at the surface. So there's other dimensions that are not shown. Maybe it involves phonon excitation of the surface, so vibrational excitation of the surface atoms, or could also involve other degrees of freedom. Maybe you can transfer energy to electronic degrees of freedom or whatever. But basically the atoms of the solid can take up energy, and that can lead to trapping. And so in that case, you would get a picture that looks like this. So you come in, you collide with the surface, you excite the surface atom motion, the energy gets dissipated, and then the atom from the gas phase can lose its energy and it can trap at the surface. Okay? But in general, you could lose energy to the phonons of the surface, or if a surface atom is vibrating at the time that you collide with it, you could also take energy away from the surface atom. You could end up scattering away with more energy than you came in. So that would be called superelastic scattering. Okay, but if just enough translational energy is taken up, then you can have, you get trapped in this potential like this. If you don't have enough energy to escape, you're going to vibrate around in this potential. You're going to collide more times with the surface. Statistically, most likely, the energy is going to get dissipated away, and you're going to end up going to a low vibrational state. Okay? And so if the surface temperature then is high enough, you can have thermal desorption, meaning if the desorption energy, right, the energy from here to here, if it's not really, really high relative to kT, then you can thermally desorb at a certain rate. And actually, we talked about that in our kinetics class, right? We talked about desorption from surfaces. Okay, what if you have a molecule? Well, then you have to consider that there's more degrees of freedom. So in addition to just the distance from the surface, you also have the orientation of the molecule, right? It matters whether, if you have a diatomic molecule, it matters whether it's coming in like this or like this, right? And there's also different surface sites where it could land, right? So, in the center of an atom would be different than, in a hollow site, for example. So you have different, basically, cuts through the potential energy surface depending on which orientation you're coming in at, which surface site you're scattering from, etc. Right? So you have a complicated multidimensional potential. And there's also more places where the energy can go. So when you scatter, in the case of an atom, you can measure the kinetic energy, right? So the kinetic energy, so the incidence energy can be transferred to phonons of the surface, right? Or you know, if that energy is taken up, then it can lose, the atom can lose kinetic energy when it scatters. But in the case of a molecule, it could also scatter and become rotationally excited or vibrationally excited. So there's more degrees of freedom where the energy can go because the molecule has more degrees of freedom that you can excite. Okay, and so there's another concept that sometimes you have a more complicated energetic situation where there could be one potential well corresponding to what's called a chemisorption and another shallower potential well corresponding to what's called a physisorption. And typically physisorption arises from sort of dispersion interactions between the molecule and the surface, so weak non-covalent interactions, and a chemisorption corresponds to a stronger chemical bond of the molecule to the surface. And there's more than one type of chemisorption. You can either chemisorb molecularly, meaning, you know, if this is like a CO molecule, then it forms like a chemical bond with the surface through one of its atoms, or you could do like a dissociative chemisorption where you break the bonds of the molecule and then you replace those bonds with strong chemical bonds to the surface. Okay? But in the case of, you know, when you have this type of potential energy surface, there's two ways that you can chemisorb. You could either directly chemisorb, you know, from the gas phase to the you know, chemisorbed surface species, or you could have what's called a precursor-mediated chemisorption, where first you get trapped in the physisorption well, and then the molecule sort of explores, you know, it diffuses, finds the right transition state, geometry to transition to the chemisorption state, and it sort of thermally goes from physisorbed to chemisorbed. Okay. Okay, so I think that's a good stopping place. The next part is we're gonna talk about how do we treat the potential energy surfaces theoretically, and then we're gonna look at an example of a reaction.